Okay, this is the common base configuration for the NPN transistor. Okay, as you can see here, the current flow, okay, from the terminal C, the collector, and goes to terminal E, and then the current from the base will flow from base to E. Okay, so from this configuration, see at the base here, the base, and this is the ground. So that's why we call common base configuration, because base is connect to the ground. Okay, so we have the input side on the left, and then for the output side at the right. So the element that is representing the output, so the IC and VCB, see here, from C terminal to B, so we call it VCB. And then for the input is IE, and then the voltage is negative B. So we check the bias. Okay, for the B and E, it is forward bias, and then for the C and B, it is reverse bias. So for this combination, we call it the transistor will work in active region. So whenever it work in active region, it will give the optimum current for the output, so which is IC. So I want to relate this configuration, relate with the graph that we call it output collector characteristic. Okay, this graph represent the output characteristic. Another name is a collector, because collector is always be a output. So remember the IC. So IC is the output now. So it represents the collector characteristic or output characteristic. Okay, so we check here. The output now is the output current is IC, and then the output voltage is VCB. As you can see from the configuration here, the IC, and then this is the graph. Okay, for the y-axis represent the IC, and then for the x-axis represent the YCB, the output. And the input, okay, this is the input that we have is from IE. So this IE, you see on the configuration here, IE is the input. So that's why we get this one. And then this is the relation for this graph. Okay, so in this graph, we have three areas, which is the saturation on the y-axis and the cutoff on the x-axis. For the active region, actually the active regions will cover this area. This is the active region. Okay, means that your current always give the best value every time it operate in this area. If the current or the voltage is around the current is around the saturation area, normally the current always shoot into the value is not fixed. Value is not fixed. Okay, so we should avoid this area. And cut off means your transistor will be off. Okay, cut off means it will be off. So the current no longer exists. It always 0. So we go to the next explanation. Okay, from the common base configuration, from this configuration, if I translate this configuration into the Kirchhoff current law, as you see in this diagram, where we get IE here, IE, and then we get IC, and then we have IB. So from the KVL, we know IE is equal to IC plus IB. So this is the equation that you must remember because it always applied on the transistor. The first equation that we get from this one. From this KCL, we see that normally the current of the IB is too small. It is in microampere. IC and IE, the current is in milliampere. So I give you example. If IC is 5 milliampere, we plus with the IB 0.02 milliampere or 20 microampere, we'll get 5.02 milliampere. So it means that IC is almost similar with the IE. And then we get this equation. This is the second equation. And this is first equation. So it proves that IE is approximate with the IC because IB is always small. Next. I want to explain about the active region, saturation, and the cut-off region. How the transistor, we will give a bias here. For the first example, I show you the transistor is in forward bias and reverse bias. And I said that this transistor is work in active region. How about the saturation? In the saturation region, it shows that this transistor is in forward bias and forward bias. Let me see the bias here. You see, N is connected to the negative of the terminal. And then P is connected with the positive. So here is a forward bias. And then on the right side, the negative, we connect with the negative. And then the P, we connect with the positive. So this is forward bias and forward bias. So we get the saturation region. For the cut-off, the transistor is in reverse bias and reverse bias. Both are reverse bias. Let me see, for the left side, the N material, we connect with the positive terminal, and then the P material, we connect with the negative. So it becomes the reverse bias. And here, N connect with the positive, and P connect with the negative. It also reverse bias. So we get the cut-off region. So every time you see this graph, especially the saturation, the active region, and the cut-off, you must remember the connection is something like this. Forward bias for the saturation. Reverse bias is for the cut-off region. Forward bias and reverse bias is for the active region. Okay. The relation, another relation for the KCL that we get from the transistor, we know that IE equal to IC plus IB. Let's say now we assume that IE is equal to IC. So if we assume IE equal with the IC, it means that IB is equal to 0. Okay. If IB is not 0, is another value like the previous example in micromilliampere something, then we can say that this equation is applicable for this one. IC equal to alpha IE. So this alpha, the value is range from 0.9 to 1. If maximum is 1, okay, it means that IC equal to IE. So it is same with the previous equation. Okay.